Hi everyone, hope everything's going well. Wanted to continue our discussion of sums of indicators, the sorts of things one can do with indicator functions, which is a lot. Okay, and that's kind of the point of this discussion. Once again, just to remind you, I have covered a lot of stuff in chapter 7 already in previous chapters. Moment generating functions aren't even mentioned until the very latter portions of chapter 7. We've been talking about that for a long time. And there are a number of other things that I've also done in the past that you will find safely embedded in chapter 7. But I think that this is a good moment to talk about just the ubiquitous nature of sums of indicators and how they can help us do a lot of things that are that were once very complicated and make them very simple. Okay, I illustrated some of that in the last lecture, and I want to do a few more things with it in this one. So let me remind you that in approximately 5 days, okay, so that would be Monday of next week, your exam is due, i.e. project on sums, okay, the sums project. You were to turn that in, just one copy with your partner. Just upload a scan and that'll be that. I hope that's going well. Please be sure to reach out and ask questions should they arise. But hopefully, I think that you'll find that it's a very helpful exercise to work through. Hope you'll enjoy it. All right, back to sums of indicators. Now, I can't help myself. I have to write an indicator this way. Okay, so suppose I have an event A, all right? Then I am going to be writing 1 sub A, okay? So the book doesn't really ever do this fully, but I'm going to do it. So 1 sub A is equal to 1 if A happens and 0 otherwise. That's it. And you'll notice things like the expectation of the indicator of A. Well, that's just going to be 0 times the probability of A complement plus 1 times the probability of A. So that just ends up being the probability of A, which is good news for us, okay? And something like this will be very helpful later on when we start to look at the number of events that occur, if I have some sequence of events that I happen to be interested in. Okay, so what I want to do is look at another example, specifically the hypergeometric random variable. So here's an example. So let X be the hypgeo. And remember, when I do the hypergeometric random variable, there's a few things I need to know. So for instance, I need to know how many balls I'm selecting, how many there are total, and how many of them are considered to be good, okay? So here's kind of the picture that I'm thinking of in my mind. Okay, so there are n total, okay, and there are m, or little m, on the good side. And there are therefore n minus m on the bad side. Okay, and then what you do is you straight up take a sample of size little n from this thing. Okay, so let's see here. Okay, so this sample of size little n is taken from this thing. Okay, we've seen this distribution before in the past. We've done a lot of work with it, but I want to look at it again through fresh eyes. I will say that I wish I had paid more attention to the hypergeometric random variable in my own probabilistic upbringing. Turns out that it was the hypergeometric random variable that ended up playing a really significant role in my own dissertation work. And so did the uniform random variables. So the project that you're working through right now is kind of, in some sense, what I deem to be important just based on my own upbringing in probabilistic tools that I wish I would have known, that I didn't realize were that valuable until the moment they became super valuable and necessary for what I wanted to do moving forward. Same thing happened with hypergeometric. I just thought, oh, this is just kind of a, unusual example, but basically binomial works all the time. Well, no. Hypergeometric does come up a lot of times in applications, and it turns out that it's super applicable, and there are really specific things that you can say about it in practice. And unfortunately, I had to learn that the hard way. So I'm trying to get you to really be comfortable with the hypergeometric, because I don't want you to suffer the same fate that I did, okay? So hypergeometric, what are we doing here? Little n is the first parameter, so that's the sample size, and little m are the number of good, so this is the sample size. M is the number of good or successful things, and capital N is the total. Okay, so once I have those three parameters, I know exactly what's going on. Okay, so remember, X is just simply equal to the number of good or successful things in the sample. Okay, and we talked about this before, but so the probability that capital X is equal to little x, what is it? So first of all, what range of values can little x be in? We'll talk about that in just a minute. But essentially, remember the denominator was just, well, I have a total of capital N things, and I'm selecting little n of them, okay? And if I have little x good things, that means that from the good side, I chose x things. And from the bad side, I chose, so there are n minus m on the bad side. From the bad side, I chose n minus x things, okay? And we talked about this in the past, but like, what are the possible values for little x? Okay, so x is equal to or less than, equal to or greater than. Okay, so what is the, what's the biggest that, what's the biggest that x could be? Well, the biggest that x could be is everything, n, okay? But the problem is, if n, like the sample size, is actually bigger than the number of good things, then the largest it could ever be is m, okay? So this is like less than or equal to the minimum of m and n, okay? And what about the smallest that it could be? What about the smallest that it could be? Well, the smallest it could be is 0, unless n is bigger than or equal to the number of, n is bigger than or equal to the number of bad things, right? The only way I could get 0 is if I could take my whole sample from the bad side, and maybe my sample is so big that it just overwhelms the bad side, okay? So, if n is bigger than or equal to big N minus m, then I would have to take n minus that amount from the good side, and that's the smallest that x could be. So what is x bigger than or equal to? Well, it's bigger than or equal to the max. Okay, I'm running out of room here, but I'll say it's the max of 0. Okay, so it's at least 0. But in the case where n is bigger than or equal to big N minus m, it bleeds over into the good side, and I'm going to have to take at least n minus the quantity big N minus m things. So n minus the quantity big N minus m things, okay? So that's kind of the rigorous range for x, okay? That's automatically kind of taken care of anyways. by those binomial coefficients upstairs. But yeah, because for instance, think about it. If I ever let x get bigger than m, then m choose x would just be 0, okay? And similarly, if n were bigger than n minus m, I would start to run into problems as well with that second. I would end up getting 0 for some values of x for that second binomial coefficient. Okay. All right. So moving on, how would I write this thing as a sum of indicators? Okay. So let's write x as a sum of indicators. Okay. How can we do that? Well, we have a couple of options, and the book presents both of them. Okay, so one of them is, basically, so here's one way. Let me just say here. So here's one possible way to do this. Okay. Basically, what I'm going to do is I'm going to actually label the good balls. So we just say let, G1, G2, ... And we can kind of think of these things as balls in an urn. Okay, how many good balls were there? So there were m of them. Let these things be the good balls. Okay. And we just let AI be the event, the ith, or let me even say this more simply. GI is chosen in our sample. Okay, that's basically the ith good ball is chosen in our sample. Okay, so how can I write x with these things using a sum of indicators? Well, x is just going to be the indicator of A1 plus the indicator of A2 plus ... plus the indicator of AM, right? It's exactly what's going to happen. The indicator of A1 is saying, was the first good ball chosen? And the indicator of A2 is saying it was the second good ball chosen. And this thing is literally going to count the number of good balls that were actually chosen. Okay, so that is interesting stuff. Therefore, look at this. I can just say things like, what is the expected value of x? Well, what is the expected value of x? Well, it is going to be the sum, right? It's just going to be expected value of the indicator of A1 plus the expected value of the indicator of A2 plus ... plus the expected value of the indicator of AM. And is there really anything different about all of these indicators? After all, all we're doing is concentrating on one of the balls specifically. Nothing is, special about one of these over any of the other ones. They're completely symmetrical in terms of their behavior. Okay, so really this is just m times the expected value of the first thing, okay, which is just equal to m times the probability of A1. Okay, and what is the probability that A1 is chosen? Well, think about it. Okay, so let's think about that for a minute. If I know that the first good ball is chosen, then all I have to do is just choose n minus 1 other balls from the capital N minus 1 balls that remain. Okay, so because remember, the probability of A1 means that the first good ball was chosen. So I'm just going to have to multiply this by capital N minus 1, choose little n minus 1, over, right? Why? Because that's how many balls I have to select and the number that I have to select from, and the total number of samples of size n is given by that, okay? So moving on, what do I get here? Let's see. So what do I get? The expected value, let me just kind of copy this down. The expected value of x, thought of as a sum of indicators, gave us this. So it was capital N minus 1, choose little n minus 1, over big N, choose little n. And this is kind of interesting. There's going to be a whole lot of cancellation that's going to happen here. Indeed, it's going to be m times, let's see, capital N minus 1 factorial over, this is the one thing that I would tell you about hypergeometrics. You end up with lots of factorials and lots of cancellation. So you just need to be on the lookout for that. And you also need to be on the lookout of how you can kind of tweak one of these binomial coefficients to look like a different binomial coefficient so that you can do some kind of trick. That happens a lot with these hypergeometrics. Okay, so what do I have? It's going to be little n minus 1 factorial. And of course, if I take the difference between cap n minus 1 and little n minus 1, the minus 1s cancel, and I end up with cap n minus little n factorial divided by, this is going to be cap n factorial over little n factorial, n minus cap n minus little n factorial. These guys cancel completely, okay? What about the other stuff here? Okay, well, actually, n minus 1 factorial, that's going to cancel completely and simply leave behind the n. The factorial thing basically goes away, and you're just left with n, because n factorial is in fact n times n minus 1 factorial. Okay, and a similar thing happens with this. Little n minus 1 factorial just cancels with that. Okay, so what do we end up with? Well, check it out. This is just m times, I have big N over little n, and I need to invert that, and it's going to be little n over big N, okay? Which, by the way, is just n times m over n, okay? And that kind of makes sense when you think about it, because m over big N, this is the proportion of good in the urn. I'm doing a sample of size n. So it makes sense that on an average, I would expect to get n times the proportion of good, number of good balls from the urn when I take a sample of size n. That's kind of like what happens with the binomial distribution. Remember, thinking of a good ball as being a success, we know there's a parallel between hypergeometric and binomial, namely the binomial is with replacement, so every ball I select, I put it back. The hypergeometric, I'm pulling out every single one and I'm not putting it back, okay? But you would expect some kind of parallels to exist. And we're not surprised in the binomial case that if I do n trials, then the number of successes I expect to be n times the proportion of success, or the proportion of good outcomes. Same thing here. The number of good or successes is the number of trials, little n, times basically the proportion of success. Okay, so even though it's without replacement this time, we still kind of end up with an average that makes sense to us, or hopefully it kind of makes sense. Okay. Now, so what I want to do right now, though, is I want to actually start looking at something else. Okay. I want to look at something else, namely, I want to look at the square of x. Why would I want the square of x? Well, because I might be interested in things like the variance, for instance. Yeah. Okay. So what about the square of x? Okay. So how would you compute the expected value of x squared? All right. Well, let's think about that. that would be the expected value of what? Well, it would be the indicator of A1 plus dot, 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 plus the indicator of A M squared, okay? You say to yourself, okay, now what am I gonna do? That looks awful. Well, what would we do? Well, it would be what? It'd be the expected value of, let's see, 1A1 squared plus dot, dot, dot. It would be the sum of all the squares of these things. Okay, plus, okay, so like I would have a bunch of products of things that aren't the same, yes? So I would have like the indicator of A1 times the indicator of A2, right? So, but I could take A1 from like the first factor and A2 from the second factor, but I could also do the opposite. I could take A2 from the first factor and A1 from the second factor. So there's going to be two of those. Do you see what I'm saying? Do you see what I'm saying? Okay. So look at this. This is going to be 2 times the sum of 1 less than or equal to I less than J less than or equal to M of the indicator of AI times the indicator of AJ when all is said and done. Okay. Now let me ask you a question. What is this? What is like the indicator of A1 squared? Well, for crying out loud, that's going to be equal to 1 precisely when A1 occurs. So that's just the same as the indicator of A1, okay? And this right here is just the same as the indicator of AM. And what about these products right here? What is the product of the indicator of AI and the indicator of AJ? What about that? Well, that's going to be 1 precisely if AI and AJ occur, okay? Which means it's the indicator of AI and AJ. So the product of indicators is like the indicator of the intersection of events, okay? Of course, the book would write that intersection as by just juxtaposing AI with AJ, okay? But I don't like writing things that way, okay? So what do we have here? Let's kind of go over to the next slide, see what's happening with that. Okay, so I get that the expected value of x squared is equal to the expected value, after expanding that thing out, it's going to be the indicator of A1 plus all the way up to the indicator of AM plus the sum 1 equal to or less than I less than J equal to or less than M, the indicator of AI and AJ. Okay. So what do you think we're going to get there? Well, you know, you can kind of push the expected value through there. Okay. Yeah. And what we're going to get is the sum I going from, or I going from 1. In fact, let me use a different letter here. I'll go ahead and use, K. K going from 1 to M, the probability, right, just by using linearity of expectation, the probability of AK, plus the sum 1 equal to or less than I less than J equal to or less than M, the probability of AI and AJ. Okay. Let me ask you a question. Remember what the AIs and the AJs were, right? Those were just, oh, sorry about that. I'm missing a 2 here. Okay, so this is 2 times this, 2 times that. Because remember, we could have done A1, A2 from the first and second factor, or A2, A1. Okay, and so we have to have that extra 2 sitting right there. Okay, now let me ask you a question. Do you think any of those individual probabilities are going to be different? Well, no, we've already talked about this. They're all going to be the same. Well, what about the probability of the intersection of 2 of these things? Are any of those going to be different? Well, no. I mean, any two of those good balls are going to be absolutely exchangeable with one another, and it's totally symmetrical. So what am I going to have here? How many pairs of events are there, I, j, such that I and j sit between 1 and m? Well, that's just the total number of subsets of size 2 from 1 through m, okay? So look at this. This is going to be m times, I can just pick out the first one, the probability of A1, plus 2 times m choose 2. And I'm just going to, I mean, I might as well just look at A1 intersected with A2, for instance. Okay. All right. So what's the probability of A1? Well, once again, probability of A1 is just going to be, well, look, I have the first good ball. Yeah, I know that that's got to be a part of what I'm doing, the first good ball. And what am I doing with the rest? Well, I just have to choose them. There's capital N minus 1 left, and I have to choose little n minus 1 other things. Okay, so it's just going to be m times what? Well, capital N minus 1, choose little n minus 1 over capital N, choose little n, okay, plus 2 times m choose 2. Now, what about this probability? Well, that means that the first and the second good ball were chosen. Yeah, first and the second good ball. I know I have those, and I just have to choose the rest. Okay, so it's going to be capital N minus 2, choose little n minus 2 over what? N choose n. Capital N choose little n. Okay, all right. Look, I've already done this computation before. Remember, this is just going to be m n over n. Yes, once I do all of my cancellation, plus, look, the 2 is just going to cancel the denominator in the denominator from m choose 2, the 2 factorial. And the m minus 2 factorial is going to cancel everything except for the m times m minus 1 upstairs. So this is going to be m times m minus 1. And what do you think I'm going to get from this second factor right here? Well, I'm going to get, look, capital N minus 2 minus little n minus 2. That's still capital N minus little n factorial. Those are going to cancel completely. In the denominator, I'm going to have an n factorial over little n factorial. And in the numerator, I'm going to have capital N minus 2 factorial over little n minus 2 factorial. I'm telling you, everything is going to cancel from the n minus 2 things, except in the denominator, I'm going to have big N times big N minus 1 over little n times little n minus 1. You're going to invert those, so same kind of game that we played before. So it's just going to be n times little n minus 1 over big N times big N minus 1. There it is. Okay, so that's interesting. All right, so look, now I can actually write down what the variance is for this thing. And all of this is because, and let me just mention, I have not even used the, I have not even used the distribution that I wrote down at the beginning at all. I haven't used the PDF at all for this thing. All I've done is I've just thought about all of these individual indicators, and I'm immediately able to write things down like the expected value. I'm about to be able to write down the variance. Okay, so let me just say, we figured out that the expected value of x squared, when all was said and done, was m times n over n, plus, and then it was m times m minus 1, and little n times little n minus 1 over big N times big N minus 1. Okay. Yeah. All right. So what is this thing going to look like in the end? Well, I can compute the variance, which is the expected value of x squared minus the expected value of x quantity squared, okay, which is this thing, mn over n plus m minus 1 n n minus 1 over capital N minus 1 minus, oh, this is interesting. It's going to be m squared n squared over capital N squared, okay? So, I mean, in the end, you end up with sort of a fierce looking formula here. But what am I going to get? Well, it's going to be little n, or little m, little n. The common denominator is capital N squared times capital N minus 1. So it's going to be n times n minus 1 plus what? M minus 1 and n minus 1. And I'm going to have to multiply this by capital N. And then what am I going to get? It's going to be minus m squared n squared. And what am I going to have left behind? Capital N minus 1. Or something like that. All over capital N squared times n minus 1. Well, there is some, there is at least one common factor I could pull out. And, but I mean, this is sort of a fierce looking formula. I would just go ahead and leave this the way that it is. The variance formula ends up being kind of ugly for the hypergeometric. Nonetheless, I was able to write it down. And it's not as if any of these computations were particularly difficult, but it is kind of an intimidating looking formula. But the thing that we are going to be able to do, and it's going to stem from what we just did by kind of thinking about like multiplying those indicators together and thinking about what's going on with those, it turns out that that is going to be the key to actually computing a lot of higher order moments, independent of the moment generating function even, because the moment generating function for the hypergeometric is kind of a mess. Okay, so that is interesting stuff. So that said, what I want to do here is look at the following thing. So what would I have if I asked for, so remember x is equal to the number of good in the sample, but really it's also the number of events A1 through AM that occur. Okay? It's the number of those things that occur, which is why x was equal to the indicator of A1 plus dot 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 plus the indicator of AM. Okay? Now, so what would I have if I did something like x choose 2? Okay, that's a random variable. Well, that's going to be equal to, if you think about it, because x, okay, just so that you think about it here, because x is the number of these events that occur, x choose 2 will be the number of pairs of events that occur, okay? So this is going to be equal to the number of pairs of events that occur, okay, which is going to be equal to what? Well, we already saw that the indicator of like AI intersected with AJ for I less than J is the indicator of the pair of events AI and AJ happening. So that's just going to be the sum 1 less than or equal to I less than J less than or equal to M, okay, of the indicator of AI and AJ, okay? Right, x2 is the number of pairs of events that occur, but clearly the right-hand side is also counting that. It goes through all possible pairs of events and counts 1 every time a pair of events happens, okay? Right, so this is just 1, I mean, think about it. Once again, this guy is 1 if and only if AI and AJ, i.e. those pair of events happen. And it's 0 otherwise. Okay? So all that to say, look, here's another thing that's kind of interesting. I can take the expected value of this thing. The expected value of x choose 2, which is expected number of pairs of events that are going to happen. Okay? And in this case, the events happen to be that I choose the good ball. That's going to be the sum, expected value of that sum, but we've already played that game. That's just going to be m choose 2 times the probability of A1 and A2. Okay? Probability of A1 and A2 means the first good ball and the second good ball were chosen. Okay, so what is that going to be in this case? Well, that's m choose 2. And what am I going to have here? M choose 2, probability of A1 and A2. We already did this, remember? It was capital N minus 2, little n minus 2. This is because I know that I have to choose the first and the second good ball, and the rest is free. And that's out of all possible selections that I can possibly make. Okay, so moving on. Okay, so the expected value of x choose 2, what's that equal to? Well, again, it was m choose 2, and it was times cap n minus 2, little n minus 2, cap n, choose little n. And we know what's going to happen with this, okay? That's going to be m choose 2. M choose 2 times what? Well, again, it's going to be n times n minus 1. That's what's going to be left after cancellation from the bottom, from the denominator of the binomial coefficient in the bottom. That's going to invert up. And what else am I going to have? Cap n times little n minus 1. Okay? And by the way, how do you think that, I mean, just kind of think out loud. What is the expected value of x? Oh, well, before I do that, let me just mention. So note, look, the expected value of x choose 2 is just the expected value of x times x minus 1 over 2. Okay, because I could just say x factorial over 2 factorial, x minus 2 factorial. And this is just equal to 1/2 the expected value of x squared minus x. Yes? Yeah. So in other words, 2 times the expected value of x choose 2 is equal to what? The expected value of x squared minus the expected value of x. Okay? And that's important because I know that the variance of x, which is the expected value of x squared minus the expected value of x with the square like this, that's going to be, if you think about it for a minute, okay, that's going to be twice the expected value of x choose 2, twice the expected value of x choose 2. And then what am I going to have to do? I'm going to have to add, right? Because look, the problem is the expected value of x choose 2 has an expected value of x squared in it, but then it has a minus e of x in there. So I'm going to have to add e of x in, and then I just have to subtract off the square of the expected value. And I know all of these things. Okay, I know this, I know that, right? If I know the expected value, of course I know square of the expected value, okay? And because I know that, and I know the previous expected values, I'm going to be able to compute the variance from that. So that might seem like a fairly, a little bit more of a simple way of doing this. So let me just kind of finish this discussion, and actually we'll stop this for now, and we'll we'll kind of ramp this back up and do a few more interesting examples with this sort of thing next time. But what if I did the expected value of x choose k? Okay. Well, what's that going to be? Well, x choose k, what is x choose k? Think about it. X choose k is equal to the number of k tuples, or k, not k tuples, it's a number of k sets of events, A1, AM, that happen. Okay. X is counting the number of events that happen, and I'm just choosing k of them. Okay, so I'm choosing k of those events that happened. Okay, so what is this going to be? Well, it's going to be equal to the expected value. What is the number of k sets of events that actually occur? Well, it's going to be a similar thing. It's going to be 1 less than or equal to I1 less than I2 less than ... less than IK less than or equal to M. The indicator of what? Okay, the number of k sets of events that happen is just going to be the intersections of this form. I1 and I2 and AIK. All right, so all k of those events happen if and only if the intersection happens. Okay, and this thing is going to count 1 precisely if those k events happen. All right, so x choose k is equal to this crazy looking sum. But these things are completely exchangeable with one another. There's total symmetry going on here. So how many total summands do I have? Well, I had m choose 2 in the case of pairs. I'm going to have m choose k here. Okay. So an m choose k. Okay, so it's going to be m choose k. All right, because I just have to choose k of those events to happen. And it doesn't matter which one I pick, right? They're all going to have the same probability of happening. So it's going to be the probability A1 and ... and AK. All right. So, and what's the probability that that happens? Well, A1 through AK happening just means I chose the first ball, I chose the second ball, ... I chose the kth ball, the kth good ball. And those are set aside, and I just freely choose the other from the other capital N minus K balls, little n minus K more. Okay, so it's going to be times cap N minus K, little n minus K, over cap N choose little n. Yeah. So what is this going to be? Well, that's just m choose K. Junk, you know, a lot of cancellation is going to happen here. But let me just write it this way. I'll write it as n minus K factorial over n factorial. Okay, times what? Times little n factorial divided by little n minus K factorial. And do you remember we had a notation for this where I have, like, if I cancel everything from n minus K on down, that was called, you know, n falling K factorial. So, like, you know, just to kind of remind you of things here, let me write this as m choose K. And what do I have? Like little n factorial over little n minus K factorial. You know, that's n falling K. And actually that looks like a put, doesn't it? Okay, so that's like n put K, if you will. That's another way to look at that. So this is P little n K. And on the bottom, this is P capital N K. right? And another way to write this is, so let me just write this over here. Alternatively, right, we have the, remember the Pochhammer symbol? The Pochhammer symbol was this, right? So cap in, you put a K like this, okay? That's just equal to P in, okay, so input K, right? And that's just n times n minus 1 all the way down to n minus k plus 1, okay? Whether n is capital or small, either one of those. All right, well, that's amazing, because if you have the expectation of x choose k, I'm telling you, and you have that for every k, you can find all the moments, all of the expectations of x to any power r. In the same way that we were able to kind of get a handle on what the expected value of x squared was by using the expected value of x choose 2, and we were able to embed that into the variance formula, okay? So this has been fairly productive, our willingness to write this random variable as a sum of indicators. We're able to come up with a lot of really nice formulas, and we never even had to write down, or we never even, we wrote it down, but we never used it. We never had to use the density for this random variable. And that's fairly remarkable. Okay, so I hope that that's convincing you of the utility of using these sums of indicators to get some interesting things. Okay, I'll talk about this a little bit more on Friday and do some nice examples. I'll do an example called the coupon collector problem. And we'll look more generally at the question of the number of events that happen. Okay, and we'll use a situation kind of like what we just did here in the hypergeometric case, and we'll develop that into a more general theory that will be very helpful to us. Okay, that's all for now.